So now let's find out about the necessary conditions for the maximization problem. So maximization of function f with several variables x, okay, subject to inequality constraint g of x less than b. So g, we said, remember, it's g1 gm. Okay, and b is a vector, constant vector bm. Okay, x is the n variables. We have x1, xn. So the minimization problem, we can study the minimization problem by, if we have, so just let's put it as a remark here, just so that you know that we are including all possibilities. So as a remark, if we had to minimize the function fx over inequality, let's say, yes, we can change also. We can have g of x greater than b. Okay, then this one is the same to maximize the function over minus fx. Okay, then take the minus, and the condition minus g of x can be changed to less than minus b. So we can always have an inequality in this direction. Okay, and we can always bring ourselves to maximization problem. Okay, because if you say that m is less than fx, okay, you found the minimum. It is equivalent to say that they have minus m is greater than minus fx. Then minus m, then minus m will be, if m is the minimum of f, then minus m is the maximum of minus f. Okay, so here I think I added the minus. Okay, yes, this is, so that, yes, it's correct. So let's continue here. So that is the minimum minus the minimum of f, okay, will be the maximum of minus fx. That does minus the minimum will be minus of the maximum. Okay, so it comes from here. Okay, this remark. So we are, by studying this set of problems, we are including the other possibilities. Now let's characterize. Our purpose is to find the characterization of candidate points. So as we previously discussed, so let's find out characterization of the candidate points. It's for optimality. As we said, when we have an inequality, we need to work on cones. And last time we established that each time we have a direction, if we have any y in Rn, such that gi prime at x star, if x star is a candidate for this maximization problem, y is less than 0 for where the contents are active, so the index are in the set I x star, then necessarily we establish that the derivative of prime at x star scalar this direction is negative. Necessarily we established this. Okay, so which is the key step for the rest of what we will do. Okay, there is an important remark I want to add here. We saw when for function C1 function, we characterized the maximum. We found the necessary for unconstrained problem where S was convex set. When S was convex, we established the characterization of maximum point as the following: negative for any x in S. Okay. Here it seems S convex. Okay. What this lemma here, above lemma inequality we are establishing here, is we are saying we are saying we have in, okay, we have now saying, we are saying f prime x at star, yes, x star, x minus x star, the y is x minus x star, is negative for any x in C of x star. Okay, we are saying that it is enough to establish the characterization, so for vectors in a cone, just a cone, a convex cone, instead of working in the whole space, you see. So which is so it's like remaining in the same concept. Okay, so now, yes, still this application characterization is not very practical. We would like to find something more practical. So without referring to this vectors, feasible directions in the cone, we would like to hide this in a practical way. So we will do that as follow. So let's introduce some notations. Okay, some notations. So this is the part. Let's now let's introduce some notations. Set A, the matrix defined by minus G prime. I, okay, x at x star for the or G with G in the set where the contents are active. Okay, so we have this matrix, big matrix, minus G1, GE1, x1, etc., GEN1, xn, etc., GEP, okay, x1, etc., we derive it, GEP, xn. Okay, and let's denote also C, the vector minus transpose of the derivative of prime at x star. Okay, so it will be the vector f1, fx1, etc., fxn minus the vector. Okay, now when we if then the application saying, we are saying here the first, if you look at this first term, so we write we write here, so let's rewrite, so or let's use the same color here, so we will rewrite this application here. So we are saying that ay, okay, ay positive, okay, ay positive, okay, imply, okay, we are regrouping ay positive, which is equivalent to say that the intersection of the set of G E prime x star y negative, okay, for I belonging to I x star. This is what we are saying. Okay, so the two writings are equivalent. Imply, we are saying EY positive, imply F prime Y negative, which is C dot Y positive. Okay, so here these implications suggest using a lemma, Farkas-Minkowski lemma. There is a lemma, important lemma in algebra. Here it is, Minkowski, Farkas-Minkowski lemma says that if we have a Pn matrix, okay, Pn matrix, okay, or we can write it as belongs to Pn, okay, matrix of R with the real coefficients here, and C is a function is a vector in Rn, okay, and then the set of Y in Rn such that EY positive includes if this set is included in the set of Y in Rn such that Cy dot product is positive, okay, then necessary there exists. So, or not then, it's equivalent even. It's more stronger. So, if each time you have something like that, then it is equivalent to say that there exists a vector lambda 1, lambda p in Rp, such lambda positive, such that, okay, such that C is connected to the matrix A by the relation T transpose A lambda. You see how there is a connection. If we have the set of vectors Y that satisfy is included in this inequality, is then necessary there is connection. Here it is, how it is expressed. And now, we will use this Minkowski. Okay, so from here, let's continue again. So from here, using Minkowski, so we can continue and say then that our C is C, which is what? Minus fx1 fxn, okay, is the transpose of the matrix. So minus transpose of GE1 x1 etc. GE1 xn GE EP x1 GEP xn times this vector lambda 1 lambda p. Okay, that is saying that f prime of x star, okay, is equal to the sum of the lambda k star, okay, g a k star of x star at x star, k from 1 to p. So you see how there is a connection which is very much better than manipulating this, the direction from the cone and inequalities. Okay, so we are close now to finish. So finally, a candidate for maximality, local candidate, will be a solution of an equation like this one. Okay, where we have more unknown, added unknown lambda. Okay, now when we take the candidate, we don't know where is it active, where it is satisfying equality. So we need to work little more here to hide also this information and work more easily. Okay, so the idea is to add the complementary slackness condition. So here it is, the idea. So, oh sorry. So if I add the complementary, so let's add the complementary, what we call complementary. Here it is, complementary. Let's introduce the complementary slackness condition. Slackness condition. It's the following one. Conditions. We will introduce, we add symbols lambda g with, okay, with lambda g, okay, lambda g equals, so our lambda are positive there, but we will choose to add 0 if we have non-equality, so strict inequality. Gg at x is strictly less than at bg. Okay, G1 to M. Like that, so we are including so the ones with that the low Minkowski lemma gives us, and the others will be necessarily 0 to yes, to say that we have then equality contrasts there. Okay, so then the other step we will introduce is the Lagrangian. Okay, introduce the Lagrangian. So function L x and lambda. Okay, so it's fx minus lambda 1 as usual, g1x minus b1 minus lambda nm gm x minus bm. Okay, and then the problem is expressed the candidate if we have a candidate. Okay, if x star, then the main theorem is the following. A theorem says that if x star is local, is a regular, yes, we need regularity, regular is a regular point and a local maximum point, okay, maximum point of f subject to the constraints to gx less than b, then there exists a unique, so there is uniqueness of this coefficient Lagrange multiplier lambda 1 star up to lambda m star, okay, such that the canonical conditions hold, such that what? So we have the gradient, so dl dxi in space x star lambda star will be equal 0, okay, equal 0 for I from 1 to n, and we have the condition lambda g, they are all positive, with the information that lambda g star equals 0 if we have strict inequality, if g x star, okay, is less than bg for g from 1 to m. Okay, so this, they are called Cohen-Cutter condition. Karush-Cohen-Tucker, I will write it. So Karush-Cohen and Tucker conditions. Okay, so they are satisfied. So this is, now you see the problem is reduced to solving a system where we don't see there's directions, etc., etc. It's much practical to do that. Okay, for the uniqueness property for the lambda I, so let's give proof of uniqueness. Okay, proof of uniqueness. Suppose that you have lambda, we have lambda and lambda primes, that is, we use the condensate proof, lambda and c equal transpose A lambda prime. Then we will have transpose A lambda minus lambda prime equals 0. Okay, which can be written as but then yes, these can be written as the sum of the vectors so lambda g minus lambda g prime and g prime x star, so we just explicit this. Okay, then here is 0, then necessarily the lambda g minus lambda g prime are 0 for g belonging to ax star, because g prime, those vectors, okay, with g belong to ix star are linearly independent. So this is the property of algebra that gives, yes, characterized what is linearly independent. Okay, great. That's all. Mainly, this is, yes, the most what you need to know. There is a remark. There are other, just to know that usually we will work with regular points. There exists other. There exists other type of regularity of points, type, types of, let's say, regularity of points where the Kahane-Dicker, Kahane-Kahn, Karush-Kahn-Dicker conditions are satisfied. Okay, are satisfied, but still we don't need to work. For example, yes, linear, if you have linear constraints, it will work. Okay, it will work. Okay, so we have this. What else? Then, yes, extensions, some extensions to other situation where we can solve problems. For example, mixed constraints. So I need to speak about this quickly. You have the details elsewhere if you want to, or either notes. Yes, mixed constraints. So for mixed constraints, so we established that we can do things like that. Mixed constraints means we are dealing with, let's say the model problem is this one, subject to the constraint. Part of it, equality, 1 to r, and with r less than n. And the other part, h k of x less than c k with k from 1 to s. So I'll give you just the theorem, then introduce the Lagrangian x lambda. So yes, x lambda and mu. So lambda and mu equal fx minus lambda for so lambda g from 1 to r of the equality constraint gg of x minus bg minus the sum mu k of hk of x minus ck, k from 1 to s. Then we will have the condition that appears dl, you will have dxi, okay, so equals 0 from I to n. We will have dl d the lambda g equals 0 from g to 1 to r, and we will have the condition on the coefficients mu k positive with mu k equals 0 if you have strict if we have strict hk of x is strictly equal inequality. Okay, for k, this is how we solve. So of course it is justified, but this is how it goes. There is another kind of problems that you can meet also, is the one with non-negativity constraints. Non-negativity constraints so includes systems where we have to solve a maximization problem subject to the constraint, let's say inequality. Okay, so we can of course and we positivity of the coordinates. Okay, x and positive. So these inequalities, we can treat them as inequalities as above by expressing minus x1 is less than 0, minus xn, and write the system at the condition as And by simplifying, we are led to then introduce, so finally it's the same to introduce Lx lambda instead of adding more coefficient mu. So it's the same to introduce only this one to reduce the number of unknowns. You see, the systems are very big, large. So if we can eliminate the number of reduce the number of unknown, it's better. Also, xi we will have equal 0 for I from 1 to n. Then we will need no, not equal 0. It will be less than. Look at this. So let's put it in red. It's less than 0. Okay. And so let's erase this part and specify in which sense. So it's easy to see it just by introducing in the proof. Okay. So and equal 0 if you have xi strictly positive. Okay. And here you do that for I to n. And we have the lambda g positive with lambda g is equal 0 if gg of x strictly less than bg, g from 1 to n. Okay, so this is the idea of how solving those categories. They are not without difficulty. Even we reduce the number of unknown, still those kind of problems are very difficult to solve. But they are the basic fundamental theorems for the theory of optimization. So that's why they are so important to know the small ideas behind, beautiful ideas that are behind of the theory, because it allows you to develop more uh, more set of solutions for specific problems. Okay.